Okay, just wanted to give you guys a quick video on determining polarity. Um, when you determine polarity, you must consider two things. You have to consider the type of molecule that you have, the geometry of the molecule, and then you have to consider the electronegativity differences. Because here's the thing, you could have a molecule that is set up of 4, 5, 6, 2, 3, it doesn't matter, bonds that are very, very polar, but they could all balance each other out and make the whole molecule nonpolar. Okay? For example, let's take a look at CF4. When I have CF4, with drawing the quick Lewis structure here without drawing in all the valence electrons, I have 4 bonds, 1, 2, 3, 4 bonds that are very polar. Um, so, but when I take a look at this thing, essentially what we can look at if we take a look at the Lewis structures, which isn't quite the right way to look at it, we should look at it as a tetrahedron. But this is balancing out this, and this is balancing out this. So the electrons don't want to go up or down. They're balanced between the two. So they'll distribute themselves evenly up and down. They'll also distribute themselves evenly left and right. So even though this is made up of 1, 2, 3, 4 very polar bonds, the whole molecule itself is nonpolar. Okay? Now, if I were to take this molecule and make a change, and I were to put Cl instead. Now, fluorine is much more electronegative than Cl is. So the electrons want to go up and not down. They're more attracted in this upward direction rather than they are in the downward direction. So this molecule now becomes slightly negative up here. This becomes slightly positive down here. And this is going to be a polar molecule now. So it all depends on what's bonded to it, and it depends on the geometry, because some geometries automatically give us polar things. Okay? So let's take a look at whether these substances are polar or nonpolar. Okay? If we take a look at NH3, which by the way should be written as NH3, I have 5 electrons plus 3. That's a total of 8 valence electrons. So we're going to draw the Lewis structure. I have N, H, H, and H. Okay? And don't forget our lone pair up there. Now, this looks like I have a central molecule, a central atom, excuse me, and 3 bonded atoms. Those aren't electrons. Those are just me pointing them out. And a lone pair. So this geometry looks like it's trigonal pyramidal. And a trigonal pyramidal molecule is always polar. So this is going to be a polar molecule. Okay? When we took a look at carbon dioxide, if we just move this up here. Oops. Hold on, let me get my black marker. If we take a look at carbon dioxide, I have 4 valence electrons plus 12 gives me a total of 16 valence electrons. So when I put oxygen on here and I give everything an octet, I notice that I have 4 electrons too many. So I'll erase some here and put a double bond in. I'll erase a couple more and put another double bond in, and now that fulfills my 16 electrons. Okay? Now, this particular case this is a very nonpolar molecule. Even though this is polar in this direction, this is polar in this direction, they balance each other out. The electrons are evenly distributed between these things, barring any London dispersion forces, and this is a nonpolar molecule, so just be careful with that. Okay, now, very quickly drawing this one, when you draw the Lewis structure to methanol, you end up with this. Actually, correctly drawn, you end up with that. Okay? Now notice this thing isn't balanced. We have these nonpolar molecules, nonpolar bonds here. Okay, we have a nonpolar bond here, but this is a little bit more electronegative in this direction, so the electrons want to come to this side of the molecule, making this side slightly negative and this side slightly positive. If we take a closer look, carbon is a tetrahedral molecule, but oxygen is bent, and bent molecules are always polar. So this polarity, this bentness here of the oxygen causes the electrons to drift over to this side and not from this side, so they drift to the right. Therefore, I have a polar molecule. All right, BBr3. If I take a look at BBr3, I end up with this. This looks to me like, and with no lone pairs around the boron. the central boron. This to me looks like it's going to be a trigonal planar molecule. And trigonal planar molecules, when I have three equal bonds, 1, 2, 3, it's going to be a non-polar molecule. Okay, so and again, just to make the argument, all I got to do is change this now to F, and I now have a polar molecule. Okay, so again, geometry, in this case, the trigonal planar molecule with three equal bonds gives us a nonpolar molecule. Okay, next, some more polar and nonpolar issues. We have CH2O. So here I have carbon, hydrogen, hydrogen, double bonded to an oxygen. Okay, so in this particular case, these bonds are not equal, and therefore it's going to be located in this direction because oxygen is more electronegative than carbon, so this is a polar molecule. CClF, here's an example that I already did before. I have, or something close to it. I have this particular example right here. So these two things cancel out in these directions. This here and this is very electronegative and towards the down position, at least in this crudely drawn Lewis structure, and therefore I have a polar molecule. SF6, again, this looks like a wagon wheel, as I mentioned before in class. I have 6 bonds, all of them pulling in opposite directions from the one across from it, so you can probably guess that this molecule will be non-polar. Okay. All right, some couple things that you should remember when you're talking about polarity of molecules is bent geometries are they're polar. Trigonal pyramidal molecules are polar, and nature likes to favor things that are balanced or uniform. Okay, so keep those 3 things in mind when you're doing these things, and I believe that is it. So you got any questions, make sure you ask.